Good morning. Today we are going to talk about the second problem, the second estimation problem, which is multicollinearity. In this problem, we are going to talk about what's meant by multicollinearity, what are the main consequences of the existence of multicollinearity, how to detect the problem, and how to overcome the problem. Number one, what's multicollinearity? Multicollinearity means it exists whenever two or more independent variables are highly correlated. When two or more of the independent variables are highly correlated. So what are the consequences of this problem? With respect to the model is still unbiased. While with respect to T ratio, will be unreliable. Because the standard error of the coefficients will be greater than what it should be. Number three, R squared would be very high, giving misleading results. Actually, OLS estimators and their standard errors are um, highly sensitive to any small change in the observations. Let's take an example. This is y, x1, and x2. These are two different examples. Let's run the regression for each one of them. For the first one, y hat equals 7.23 plus 0.5 x2, sorry, x1 plus 0.06 x2. Standard errors 0.39, 0.05, 0.02, and with respect to t, 18.57, 9.3, and 3.58. And in this case, r squared is 0.99. While in case number 2, y hat equals 7.63 plus 0.8 x2, sorry, x1 plus minus 0.1 x2. Standard errors 1.57, 0.4, 0.13, t ratio, and finally r squared is 0.81. If you are going to compare the initial data or the actual data, you can find that there is only one difference between the two examples, which is this observation. In example number 1, it's 9, and in example number 2, it is 7. Although there is a huge differences in the regression model. As in the first case, all the variables are significant based on the value of t. R squared is 99%. x2 is positive, affect y positively. While in example number 2, we can realize that x2 is insignificant. x2 has a negative impact on y, and r squared decreased to 0.8. So the value of the parameters and the standard error are highly sensitive to any change in the observations. So as a result, if there is any change in the observation, this will affect the parameters and r squared, and will affect reliability of the results. So in case of the existence of multicollinearity, we will not be able to trust the estimators. We are not be able to trust the value of the parameters. So how to detect the problem? Number one, there are 3 different tests that can be used in order to detect multicollinearity. Number 1, high R squared coupled with lower values of the T ratios. Actually, T ratios shows the significance of the parameters. So if they are insignificant, this means that the variable has no significant impact on y. And R squared shows the significance of the model, including the variables. So if they are high, this means that the variables can affect or have an important portion of the explain a huge portion of the variation in y. So there is a contradiction in this case. Y, say for example, y equal to 24.77. From this model, you can find that x2 has an insignificant impact on y. So we are going to reject h1 and accept h node. And in case of x2, also it has an insignificant impact on y. So this means that x2 and x3, both of them are insignificant. And at the same time, r squared shows that the model, which mainly is x2 and x3, explain 96% of the variation in y. So this is an indicator of the problem of multicollinearity, as there is a contradiction between the significance of each variable alone and the significance of the whole model. Indicator number 2 for the detection of multicollinearity is the existence of high correlation coefficient between two independent variables or predictors. So this means if you are going to find r, not r squared, r between x2 and x3 is gonna be high correlation. And number 3, auxiliary regression. Auxiliary regression shows that regressing one predictor on another yield highly significant results. This is an indicator also for the high correlation between two predictors. So if we are going to take the same last example and find the auxiliary regression in this case, it will be, now we are going to make a regression for x2 on x3. This is the auxiliary regression. As you can witness that the r squared in case of running regression for x2 on x3, it's 99.8%. And if you are going to do the same with respect to x3, And also, if you are going to run the regression for x3 on x2, it will be 99.8%. Now we are going to make a regression for y on x2 and y on x3, which means that we are going to drop one of them in each estimation. The results indicate that each independent variable is positively significantly affect y. But in the original situation, x3 has a negative impact, not a positive one. So this is an indicator. Also, if you are going to compare the value of r squared, you can find that when you are going to run regression for x2 over x3, it is very high, r squared 0.998, which is much more higher than y on x or x2 or x3, and much more higher than the original estimation. So these are the three main indicators for the problem of multicollinearity. So after detection of the problem, we would like to cure this problem. So how can we overcome this problem? Remedies of multicollinearity. Number one, to do nothing. In some cases, you cannot collect more data. Actually, multicollinearity is mainly a data deficiency problem. So in sometimes you cannot make any choice over the data, you cannot collect any more data or change it. So it's gonna be relevant to do nothing, just to make an interpretation that there is a multicollinearity problem, and that's all. Number two, dropping a variable. It is common in case of severe multicollinearity to simply drop one of the variables that causes the multicollinearity problem, or the highly correlated independent, one of the highly correlated independent variables. But actually, dropping one of the variables may cause another severe problem, as you can drop one of the most important factors that affect the phenomena under consideration. So you must be very careful during dropping one of the variable, that this drop or this omission of the variable will not affect the economic model itself. Number three, actually this is the case of dropping one of the variable. In this case, we dropped x3, and in this case, we dropped x2. Number three, variable transformation. take an example for a Cobb-Douglas production function. If you would like to estimate this Cobb-Douglas production function, actually this is a non-linear model in variables, not in parameters, and we can estimate it using OLS, but after converting it to be in a linear form. So in order to be able to estimate it, we are going to use log for the whole model. So now this is the linear form of the model, which can be estimated using OLS. After estimation, this is the results after estimation of the model. The results are not in line with the expectations of the economic theory. The theory states that both labor and capital must be positive. And have a significant impact on Q, while actually K has no significant impact on Q, and R squared at the same time is very high. So this is an indicator of a multicollinearity problem. Of course, we can run an auxiliary regression in order to make sure that there is a problem, or find the correlation coefficient between L and K. Actually, after doing all of this, we realized that there is a problem of multicollinearity, and we would like to overcome this problem using transformation of variables. Transformation of variables can be done in the form of division. Divide the whole model by one of the variables. So we can write our model after transformation like len Q over L equal 3.77 plus 0.48. Sorry, this is log K over L. Standard error is 0.68 and 0.15. T ratio is 5.56 and 3.2. R squared is 0.51. So the values of the estimated parameters are consistent with the theory in this case. So this is considered to be a solution for the multicollinearity problem. The last solution that can be used is adding new data. As we said, multicollinearity is a data or a sample problem. So one of the possible ways in order to overcome this problem is to increase sample size. So let's assume that in the previous case, the number of observations was 12. And now we are going to re-estimate the model with a greater number of observations as we increase the number of observations from 12 to 40. So after estimation, so this is the model after re-estimation of the model using a greater number of observations. We can find that K has a positive impact, which is consistent with the economic theory, and R squared is lower than the initial one, which has a problem of multicollinearity. So adding more variables, adding more observations solved the problem of multicollinearity. You can perform more than one technique, as you can add data and make transformation or something like that at the same time, but never deviated from the expectation of the theory. You have to focus on the economic theory while making any modification for the model. This is the end of our lecture today. Thank you, and see you next week.